In this video, I'm going to do an example of how to solve for slope and deflection along a beam using the direct integration method. So this is basically using the Bernoulli-Euler beam theory and the integrals that come out of that theory to determine slope and deflection as a function of x along the length of the beam. And so in design handbooks, you might typically find a table that has a lot of different situations given in terms of general dimensional variables, for example, like L and A, so that for any given example that looks similar to this, you can come out with the slopes and the deflections very easily just by subbing into some equations that come out at the end. So we're going to find out how to derive equations like that for this example, and this is on the tricky side for an example like this, so you should be able to apply this method to other similar types of problems. So the first step is we need to find the reactions as a function of the input variables P, which is a general load, A, which is a length, and L, which is another length. So if we just draw our situation here again as a free body diagram, then we have the unknowns at the pin, AY and AX. We have BY, which is the vertical reaction at the roller, our applied load P, and then two lengths. This one is A, and this one is L. I mean, it's just right above there. So I don't know why they're really redrawing it. But anyway, so start with sum of moments, as usual. Should be quite practiced at this kind of problem. So we have sum of moments about A, okay, over here. So we have BY times L minus, because this is clockwise now, P times L plus A, which is the total length, equals 0. So it's exactly what we were doing before, except now we're working with unknown constants instead of known geometric dimensions. So if we reorganize this, we get P L plus A divided by L. Could also write this as P 1 plus A over L, and this is positive in the vertical direction, going up. Sum of forces in the Y equals 0. So we have AY plus BY minus P equals 0. So then we sub in what we had for BY, which is P times 1 plus A over L minus P equals 0. So this P and this P times 1 cancel out, and we get AY is equal to negative PA over L, which is PA divided by L in the downward direction. And then sum of fx equals 0 gives ax equals 0. Pretty common. Okay. So now that we know our reactions, we can start by finding a general equation for the moment along the beam for which position x. So we know that the moment for AB is going to be different than it is for BC because we have this reaction here that's going to change the shear. So we have to do separately what's the moment between AB as a function of P, L, and X, and then what's the moment BC as a function of P, L, A, and X. So we have a new free body diagram, and it looks like this. So we know PA over L now, and we know this is P1 plus A over L, and we have P, this is still L, and this is still A, right? And this is point A, B, and C. Okay, so if we look at segment AB, okay, so this is, if we take x, so we're gonna say that x equals 0 is at A, and then x increases from a. So if x is between 0 and L, then we're on segment AB. And what we do is we just take a cut at general position x, which is between A and B, and so we get a free body diagram that looks something like this. Okay, so this is A. Okay, this is x. This is our beam, right? So we still have PA over L, and then at our cut, since we're cutting in the middle of a beam, we have a horizontal load, we have a vertical load, and we have some sort of moment. So this is the internal moment in the beam at point X. Now we're not really concerned about this shear and the axial. Since we're talking about deflected shape, all we really care about is the moment. So we take a sum m about x equals 0, and we'll say that counterclockwise is positive. So now we have mx plus PA over L times x, because now PA over L is x distance away, equals 0. So then mx equals negative PAx over L. So we know that it is PAx over L in the clockwise direction because we've done it counterclockwise. Now, in general, we're going to use this formulation since we're going to integrate. We want to keep track of the moments in their absolute positive or negative form. So you want to recall, if we're talking about moments, our sign convention is like this. So if we have a moment that's causing a positive bending effect, then on the right side of that beam we're going to have a counterclockwise, and on the left side we're going to have a clockwise. So since this is a clockwise moment, then it is negative. So we're going to use this as negative. So if we were to draw this moment on the moment diagram, and we draw on the compression side, then this is going to be below the beam on the moment diagram. So it's causing a bending downwards, concave down. Okay, so now that we have our moment, we can determine our curvature. And our EI is constant. So we have curvature, that's phi, right? It's d squared y over dx squared, which equals m over EI. So this is our Bernoulli-Euler equation. And so m over EI is equal to p negative PAx over EI. That's very simple. So now that we know our curvature, if we integrate our curvature, then we have an expression for the slope. So here's our slope, theta, right, is the integral of negative curvature, which is PAx over EI. Oh, I'm sorry, I forgot an L down up here, because this was PAx over L, so PAx over LEI. Okay, dx, and if we solve that, get negative PAx squared over 2 LEI plus C1. Now you'll recall, if we're talking about a moment area theorem, the moment area theorem only gives us relative slopes depending on the area under the curvature diagram. So we need to know the absolute value of the slope at some point in the beam in order to find the value of the slope at another point in the beam. Now this is a little bit different. We're doing an integration, so we're still finding the area. This is effectively the area under the MEI diagram. However, this C1 accounts for our boundary condition. So this C1 accounts for the fact that the slope is not 0 at point A. And we have to find that C1. We have to solve for it using the boundary condition. So this is kind of like similar to in the moment area theorem, we need to find a reference tangent so that we have some reference value to compare against. But in this method, we find the constants of integration and we use the boundary conditions to evaluate them. So now if I integrate this again, So if I'm now integrating the slope, then I can determine the deflection, which is y. So y here is negative pa x squared over 6 lei, right? Because x squared over 3, sorry, x cubed over, sorry, x cubed. I integrate x squared, I get x cubed over 3, so this is x cubed over 3, so that's why we get the 6, plus c1x, so c1 is a constant, so integrate it, we get c1x, plus c2, which is the constant of integration added due to the second integration that we're doing here. So now, as I said, we want to evaluate our boundary conditions in order to find these constants. Okay, so we know two boundary conditions for this part of the beam. The first one is that at x equals 0, where the pin is, we have 0 displacement. So y is equal 0. So x 0, y equals 0. And then at this roller, we also know, so when x equals L, which is the x position of this roller, the y is also 0 because it can't displace up and down. So we have 2 at x equals 0, y equals 0, and I'll say boundary condition 2 is x equals L, then y equals 0. So this one is the pin, and this one is the roller. Okay, so now if we evaluate 1, okay, so we use our equation for y. So recall our equation for y. Now I'm going to sub in x equals 0 and y equals 0. So we get 0 equals negative pa x cubed over 6eil plus c1 times x, which is equal to 0, plus c2. So these both go to 0 because they have 0 in the numerator, so therefore c2 equals 0. Okay, and then if I do the same thing at x equals L, I get negative pa L cubed over 6 lei plus c1L plus c2, right, which is 0 we just determined. And we rearrange this for c1, then we get c1 is pa L cubed over 6 lei times 1 over L, which is from the c here, and then we get c1 is pal over 6ei. Simple. So then now that we've solved for both of those constants, we can re-sub these into the equations for slope and for deflection. So we know that between 0 less than or equal to x less than or equal to L, theta equals, so this is the original part, and this is the constant c1. So then if we rearrange this for theta, then we get this equation. So then I just simplify it and collected some like terms so that I can factor them out and make the equation a little bit simpler. So now we do the same thing for y. So now this is the original part. This is c1. This one is c2, which is 0. And then we rearrange and collect, and we get this final equation for y. So this is just for the first half of the beam. Now we have to repeat this process for segment BC. So if we have segment BC, which is between L and L plus A, which is where the end of the beam is, now I'm going to just take this cut at x, except now where x is between B and C. So here's our beam. Okay, here's A, here's B. Okay, x comes all the way out to this cut here. This is A. Okay, so we still have the same PA over L, But now we also include this vertical reaction in B, which we didn't have before because we were to the left of it. Okay, and again, since we have a cut here, we have horizontal, vertical, and a moment. And that moment is m at x. So now if I solve for this moment, by taking equilibrium about mx, we get mx minus p 1 plus a over L times x minus L. So that's the distance here. So the total distance is x, this distance is L, so the distance from the x location to B is x minus L. And then plus PA over L times x equals 0. So then I am expanding this equation and collecting the like terms. These ones drop away because they're equal and opposite, and then we end up with this expression for mx. Okay, now again we go through the same thing. We find the curvature. Okay, so this curvature, which again is d squared y over dx squared, equals m over ei, which equals, we just have p over ei, x minus L minus a. And now if we solve for the slope, just the integral, with respect to dx, then we get p over ei, x squared over 2 minus lx minus ax, and we have a constant of integration, we'll call that c3. And then we integrate that one more time to get y, and we get x cubed over 6 minus lx squared over 2 minus ax squared over 2 plus c3x plus c4, which is our new constant of integration. And now again, we use our boundary conditions, and the boundary condition here is a little bit different. Okay, we have 1, which is obvious because we have our pin. So our roller at x equals L, y equals 0. Yeah, let's go over here. So that one's pretty obvious. At x equals L, y equals 0 because of the pin. But at C, we don't have anything else. We don't have any boundary condition here. But we do know that at B, since this is a continuous beam, then the slope has to be continuous as well. So the slope that we got from AB, so the slope at B, has to be the same on this side as it is on this side. So we can say that at x equals L, the slope equals PA over 2EI negative 2L over 3. And this is just a simplification of the value that we got from the other side. Because what we had before was this, if I sub L into this equation, then this simplifies to this. Okay, because that's the slope at that point. So now we use that. So here's PA over 2EI negative 2L over 3. So this is theta. So in the theta that we derived, on the theta side here, this is where I've subbed in our previous theta from the other side. And I say equals. Now I'm going to put in our current value for theta, where x is equal to L. And we get this expression here, subbed in for L. Then I'm going to rearrange for C3. And I get this final expression after collecting the terms and refactoring it. Okay, so we know C3. Now we can use our boundary condition 1, which is just y equals 0 at x equals L. And we have P over EI. So this is basically our equation for y that we have here, where this part stays the same, sub in L for x, sub in C3 here, and L for x. And then we're going to solve for C4. So then collect and rearrange for C4. And after I collect all the terms and factor it out to make it a little bit cleaner, then I end up with this expression, and you can double check for yourself that that's correct. So now that I know those boundary conditions, C3 and C4, I can sub them back in to find theta. And again, after we collect everything together, we can't simplify it very much, so we end up with this big equation, and that gives us theta between x equals L and x equals L plus A. Then we do the same thing for the displacement, where this is the original main part of the y equation, then this is C3, this is C4, and we can collect all the terms, and then we end up with this big expression. And we could maybe simplify this a little bit more, but probably not too much. We can maybe take the L and the x out and put some on the bottom. Alright, so that's your expression for y. So now, using those 4 equations that we found, 2 for slope and 2 for deflection, we can find out the slope and deflection of any point along any beam with an overhang that looks like this, where we know L, A, and P.